let's take a look at the following theorem. The transpose of AB equals the transpose of B times the transpose of A. In this video, we're going to present the proof of the theorem. We begin by assuming that the multiplication is defined. So we take our dimensions of A and B to be compatible for multiplication. So let A be an M by K matrix, and let B be a K by N matrix. We're breaking down our proof into two goals. So we aim to show that, one, the dimensions of AB transpose and B transpose A transpose are the same. And in our second goal, we want to show that the generic entries of AB transpose are identical to the generic entries of B transpose A transpose. That is, the ij entry of AB transpose will be equal to the ij entry of B transpose A transpose for all I from 1 to n and j from 1 to m. Okay, so let's deal with the first goal. What are the dimensions of AB transpose? A, B transpose. Well, we know that A is an M by K matrix, and B is a K by N matrix. So that's given. This multiplication is defined because the inner dimensions are equal. So that product AB is an M by N matrix. That's by multiplication of matrices. That means its transpose is N by M. N by M. Okay, now let's go and find out what the dimensions of B transpose A transpose are. So again, B is K by N. Consequently, its transpose has to be N by K. The dimensions of A are M by K, so its transpose is K by M. So now we're multiplying two matrices. The multiplication is defined because the inner dimensions are equal, and the result is N by K, N by M. Okay, so our first goal is complete. This left-hand side and the right-hand side of our intended equality have the same dimensions. Okay, so our second goal. We want to show that the ij entry of AB transpose equals the ij entry of B transpose A transpose. Let's find out what the ij entry of AB transpose is. Okay, so let the transpose of AB be the matrix that has entries Cij. Now, Cij, the entry Cij, is the dot product well, let's begin with this. Cij is the ij entry of AB transpose. So is the ij entry of AB transpose. That means that it has to be the ji entry of AB by definition. So, which is the ji entry of AB. This is by definition of transpose. The ij entry of the transpose is the ji entry of the matrix you transpose. Okay, so what is that? Ji entry of AB. Well, by definition of multiplication, the ji entry of AB has to be the dot product of the jth row of A in the ith column of B. So I'm taking the dot product of the jth row of A and the ith column of B. Okay, so let's see what they are. The jth row of A is AJ1, AJ2, all the way up to AJK. The ith column of B is B1I, B2I, BKI. So let's compute that dot product. AJ1 times B1I plus AJ2 B2I plus AJ3 B3I plus plus AJK BKI. Okay, so that's the ij entry of AB transpose. Now let's go ahead and compute the ij entry of B transpose A transpose. Okay, so we want to find out what the ij entry of B transpose A transpose is. So let B transpose A transpose be the matrix whose entries are D, I, J. So we are after finding the I, J. Now, by definition of multiplication, the I, J is simply the dot product of the ith row of B transpose and the jth column of A transpose. But if you're looking for the ith row of B transpose that is the same as the ith column of B, the entries of the ith row of B transpose are the same as the entries of the ith column of B transpose. So I'm going to get a row. This is a row, so this is the ith row of B transpose. So it's going to look something like this. It's going to be a row matrix. But these entries that you will find here will have to be those B1I, B2I, all the way to BKI. Now, now we want the column matrix. So the jth column of A transpose, if you're looking at the jth column of A transpose, that had to be the jth row of A. Again, the jth column of A transpose had to be the jth row of A. The entries, let me clarify, the entries of the jth column, which is a column matrix, the jth column of A transpose, the entries there will have to be the same as the entries of the jth row of A. But we already know those are AJ1, AJ2, all the way up, all the way down to AJK. Okay, so let's compute that dot product. So we get B1I times AJ1 plus B2I AJ2 plus B3I AJ3 plus and so on up until BKI times AJK. Now, let's do the following. Let's say these are all scalars. These are real numbers. So we know that multiplication of real numbers is commutative. So let's do the following. Let's commute the A's and the B's. So B1I AJ1 is the same as AJ1 B1I. And then plus a B2I AJ2 is the same as AJ2 B2I plus B3I AJ3 can be rewritten as AJ3 B3I plus and so on up to the last one. We can rewrite BKI AJK as AJK times BKI. Now, so these are our entries. These are the IJ entries of a B transpose A transpose. Let's compare those results. So the IJ entry of a B transpose and the ij entry of B transpose A transpose are equal to each other. Observe aj1b1i, aj1b1i plus aj2b2i plus aj3b3i plus and so on up to the last one, ajk bki. So our second goal has been achieved, has been completed. So the proof is complete. Thank you for watching. That's all for now.